Differential equations, 5.1, day 4. We have a second day, day 2, of free damped motion. This problem has a little bit of a twist to it. It's kind of a nice little twist. Let's read it. It says that a mass weighing 16 pounds is attached to a 5-foot-long spring. At equilibrium, the spring measures 8.2 feet. So here's something that we can begin to just draw out and think about. When there's no weight, there's no mass pulling that spring down, it's 5 feet long. However, when we do put a mass on it, at equilibrium, remember that would be the resting point, all of a sudden this spring is stretched out 8.2 feet. Now, we can talk about the distance that the spring has moved from 5 feet to 8.2 feet. That's 3.2 feet. So what are we really seeing? We're very much accustomed to having a problem where we're told a certain weight will stretch the spring so many units of length. In this problem, right from the beginning, guys, we have to be careful. We have to read very carefully and get the information from the context that really a 16-pound mass will stretch a spring 3.2 feet. So going from 5 to 8.2. So it stretches 3.2 feet. And that's what a 16-pound mass does. So how does that come into play? Well, it should remind you of Hooke's law. So Hooke's law, we can say, well, the force, which is the weight right here, would be some constant multiplied to the distance. And, we can say, hey, we've got our 16-pound force, and we're seeing that the spring is stretched 3.2 feet. Of course, we can convert 3.2 into a fraction and then divide, but for the sake of time here, and we can have a calculator in front of us, it would only take a moment to take 16 divided by 3.2 and to get 5. Remember, 5 is a very important answer here, that K is what we are looking for. You might remember that K is so critical. We need to know that. We also need to know M, the mass. What we can go back to is from Newton's second law, F was equal to ma. We can say that the weight, that's a force, would be the mass times the gravitational constant. And, we've got a 16-pound weight here. We're looking for our mass. The gravitational constant, where downward is considered positive, would be 32 feet per second squared. We can divide by 32. And look at this. We haven't even read through the full problem yet, but we're getting very, very important information here. Why is that so critical to have K and M? Well, we talked about this just the other day, that, what do these damped motion differential equations really look like? Well, it's the second derivative of x with respect to t. We'd have beta all over m, dx dt, and then we'd have k over m, x is equal to 0. And wow, right now, knowing k and knowing m, that's fantastic. You might wonder what beta is, and we'll try to piece that all together as we work this through. So it's saying at equilibrium, the spring measured 8.2 feet, but it says if the mass is initially released from rest at a point 2 feet above the equilibrium position. Wow, that's two very important initial conditions. First of all, it's released from rest. That means its velocity at time 0 is 0. Oh, that's a subtle piece of reading right there. We pick up from rest means our velocity is 0. And remember that downward is positive and upward is negative. So when we're releasing from a point 2 feet above the equilibrium point, we can say that our beginning position, x sub 0, would actually be -2. And then it says, find x of t in both forms. We're going to review a lot today. We're going to go to the form with the 2 trig functions, perhaps, with cosine and sine, and then condensing into one. If the surrounding medium offers a resistance numerically equal to the instantaneous velocity. Remember, beta was that constant towards the instantaneous velocity. And what we're seeing is that resistance is equal to that. Because it's equal, beta would equal 1. So the resistance would be 1 times the instantaneous velocity. So again, quite a bit of reading that is coming into play right now. Let's go ahead and create our differential equation, though. We'll have our second derivative of x with respect to t. Our beta, we just saw, is 1. Our m, well, wow, we just found that to be 1/2. And there's your dx dt. Our k, we saw, was 5. And without too much work here, we're going to be able to get our differential equation and hopefully be able to solve that very, very fast. 5 divided by 1/2 is 5 times 2. That's a 10. Wow, look at this. And of course, we have our 2 initial conditions here as well. So we're going to have to find those constants. Well, at this point, I hope what you can do is very quickly realize we have a characteristic equation. And, right here you can see that we have a quadratic equation. For the sake of time in this video, I'm not even going to go ahead and type into the 89 or work out the quadratic formula by hand. You can do that. You can definitely do that. For the sake of time, though, let's just realize that if you were to solve that quadratic via the TI-89, preferably with a C solve, you'd get -1 plus or minus 3i. And at this point, that's going to lead us to the general solution. This is kind of like our alpha and beta. We'd have e to the -1t, and then we'd have c1 cosine of 3t plus c2 sine of 3t. And wonderfully at this point, you can pretty much realize that you can now solve for your constants. Let's do that. Let's first see what's happening if we plug in t equals 0 and we get a position at -2. So if we did that, it would only take a moment to do that. You'd have a e to the 0 right here, and of course, cosine of 0 is going to get you a 1, and the sine of 0, well, wow, that's just going to be a 0. Canceling out your c2. E to the 0 is 1. It should only take you a moment to know that your constant c1 is actually equal to -2. Now, by the way, what you can do at this point, you are more than welcome. You see, this is no longer unknown. This is no longer an unknown part of our equation. We know what C1 is, we just don't know what C2 is. So you look right here and you'd say, well, hey, this is wonderful. We're getting there. We just need to use our other initial condition. And, of course, as we do that, we can see where we're going. We can say, hey, we're going to need to say x prime of 0. That was equal to 0. Remember, we were told that we were starting from rest, and that's really saying that your velocity is 0. So to take a derivative, guys, we're going to have to actually go ahead and use the product rule. Now, if you wanted to, there's so many different ways you could do that. You could, of course, just consider u to be the e to the negative t and consider v to be this trig expression. Let's go ahead and do that. And we'll have x prime, and this would be your u. Let's not take that derivative just yet. And then take our derivative inside. Well, the derivative of cosine is negative sine, but the chain rule, out comes a 3. So a negative 2 times 3, you should get a 6 sine of 3t, right? The derivative of sine is cosine. So with the chain rule, out comes a 3. So we'd have this. And then, that's your uv prime. Then we want to take u prime. U prime would be negative e to the negative t, taking the derivative of our e to the negative t here. And then we're just going to multiply it to that, negative 2 cosine of 3t plus c2 sine of 3t. So what's going to happen? We're plugging in a 0, for our t. E to the 0 is just going to be a 1. Sine of 0 is going to completely cancel out. Cosine of 0 is a 1, so it looks like I'll have a 3c2 from this point. When I plug in my 0 here, now be careful. We've got to realize that, yeah, you get e to the 0, but that's going to be a negative 1 right here. The cosine of 0 is a 1, so we're just going to have negative 2 times 1 is negative 2. And the sine of 0 just completely goes away. So, wow, we're almost done here. We could say 3c2. A negative times a negative is a plus. So, you can subtract a 2, divide by your 3, and you'll get negative 2/3 for your c2. Now, I do want to just point out to you again that ultimately we already had up here what our equation should look like. Right now, we just have to go ahead and put this all together. We'd say, well, what is x? X is going to be e to the negative t, negative 2 cosine of 3t, and then we've got our negative 2/3 sine of 3t. By the way, that's a legitimate answer. That's a wonderful answer. However, they did ask for the other form. When they said both forms, what they're really saying is, could you also get this down to just one trig function? And, that other form would be, could we get a sine of our 3t plus this angle phi, right? And here we have our c1, and here's our c2. Right, so real quickly, let's just finish that up. We could say, well, we knew A was equal to C1 squared plus C2 squared. And very fast, we can work that out. We'll have negative 2 squared plus this negative 2/3 squared. And that's going to be a 4 plus 4/9. And, just real quickly, getting this to work out, 9 times 4 is 36, so that's 36/9 plus 4/9. That's the square root of 40 all over 9. Well, we know that the square root of 9 is 3. The square root of 40 is 2 root 10. So, wow, we're well on our way to finishing this up. But what else do we have to do? Well, real quickly, we're just going to have to find what phi is. And it looks like we're just about to run out of time. So we're going to have to finish up the video in just a moment with that.